Okay, so here's where we were. So we were talking about Gauss's divergence theorem, but more specifically some, applications of Gauss's divergence theorem that come up as a result of the fact that this is the boundary theorem that involves three-dimensional things in a three-dimensional world. And being as we are three-dimensional things in a three-dimensional world, no surprise that there are lots of applications to physics here. The question that we entertained last time came up with some powerful results. Is if you have a boundary, three-dimensional, boundary of a three-dimensional thing, so a two-dimensional surface, the boundary is, and you're interested in the flux. So that's what we're going to be interested in, is flux through boundaries. Right? Interested in flux through this boundary. Okay, what about the mass? What about a piece of mass that's on the outside of the surface? And the answer, it contributes nothing, right? You might say in some sense that every bit of flux that flows in just flows right back out, in effect. And grand total, no flux. Okay. What about mass that's on the inside? Now here's that same surface, right? And it's a boundary of something, and I want to know how much does a piece of mass inside of the region, how much does that contribute? Well, okay, so we'll talk about that later to get an exact answer. But what we were able to conclude by a clever argument that involved sort of hollowing out a little cavern, around the mass, is that the mass itself is all that matters, and where the mass is doesn't. So if the mass is there, you hollow out a little cavern, make a little sphere, you get the same flux. And on the other hand, if the mass were up here, as long as it's the same amount of mass, you hollow out a little cavern and you make a sphere and you compute the flux and you get the exact same value. Right? So the big conclusion from this second argument is that only the amount of mass, not the distribution of mass inside of your boundary surface matters. Now, how it matters, what exactly is the relationship between mass and boundary flux? Yet to be determined. We'll get there actually pretty soon. Okay. So, then we consider now a third question, and the third question is preposterously difficult. So it seems, we have some distribution of mass, and it's, there's a dense spot over here where there's a lot more mass and maybe a little bit of a density down here, and it's it's just a varying density of, a cloud, varying density of mass distributed all over. Each particle of which creates a gravitational field. So we're no longer talking about a single particle inside or a single particle outside, but bazillions of particles, each one of which creates a gravitational field, the sum of which is preposterously difficult to write down. And then we're going to consider the further question. I'm not even going to constrain the question to what is that gravitational field, but furthermore, what is the divergence of that gravitational field? Insanely intimidating questions. And it turns out the answer is surprisingly easy to get to by a clever argument. We're going to look at a point. I'm going to attempt to compute the divergence of the gravitational field at that point. And the way I'm going to get at it is by drawing a little ball. Around that sphere. We're going to consider this solid ball. We're going to consider its boundary surface, and I'm going to ask a related question, not the original. The original question was, what's the divergence? We'll get to that. We're going to consider a related question. Let's talk about the flux through that surface. And strategically, here's the big idea, and mathematicians do this kind of thing a lot. If you have a hard problem, don't head straight at it. It's hard. That doesn't make sense. You're heading straight at an impossible problem. That's impossible. Right? Pick a related problem. Answer the related problem. Choose the related problem to be a problem that where you have tools to work with that are going to make that related problem easier. Once you know the answer to the related problem, then look for ways to connect that to the original really hard problem. So divergence we don't have a lot of tools about that yet, but flux, we have tools. Look, here's one of the big tools we have. We have a tool that says that if you have mass outside of your boundary surface, that mass on the outside doesn't have anything to do with the flux. It contributes 0 to the flux. Throw that mass away, doesn't make any difference to the flux. Mass that's on the inside of your surface, you can't throw that away. Okay, sure, that's fine. But you can move it around to your heart's content. Knock yourself out. Move it around inside that surface any way that makes your life more convenient. So here we have this related problem: the flux around this little, the flux through this little sphere around that tiny, that one point that we're considering. Flux relates to divergence, right? Gauss's divergence theorem. So this is a related problem. We have tools to consider flux, and the powerful first simplification is that all this mass on the outside of that sphere, bye-bye, gone. It doesn't matter, right? Next simplification, all the mass that remains that's on the inside of that sphere. Okay, I can't throw it away, but I can redistribute it however I'd like, and I'm going to take all of this mass that's on the inside of that sphere. I'm just going to compress it all down, putting a point mass exactly at the center of the sphere, because that's easy to deal with. Okay, so these first two conclusions that we came to were tremendously valuable already. Okay. All right. Now, considering back to this question, we have a point mass now. Let's see if I can actually erase that little bit. Okay, and I need to get this in the right mode. There we go. Okay, so we have this point mass, and I'd like to talk about the flux of that point mass gravitational field through this boundary. Okay, the calculation here is pretty straightforward. Going down to the next page here. We're interested in computing flux, remember? There's our general formulas for flux. And I'm going to use the formula that says F dot N ds. Now don't forget our picture. We have a little sphere. This is a small sphere that's going around a single point mass. And I want to compute that flux. Let's see. So now, according to this formula, I need to talk about the unit vector. That unit vector in, well, handy formula for that unit vector. This is a sphere. Spheres have tons of symmetries, and one of them is that the outward pointing unit normal vector is x divided by magnitude of x. Right? Again, spheres are symmetric. Okay, we've pulled that trick previously, so I hope you all remember that one. The formula for the gravitational field, well, we already have that. There it is. Gravitational field created by a single point mass. Whoops, circled too much. Created by a single point mass is that. So, just kind of plug in for the specifics of this problem, and out comes what is now just an algebra problem. Just need to compute this surface integral, and notice a lot of good things happen here. First good thing that happens is we have, let's see here, I guess I'll circle this in purple. We have x dot x, that's magnitude squared. So magnitude squared divided by magnitude to the fourth gives us 1 over the magnitude to the fourth, 1 over the magnitude squared, and so that is just r squared. Further notice, yes, that integral was being done over this entire sphere. Position depends on where you are on the sphere, but the sphere has this another wonderful symmetry, convenient fact that every point on the sphere is exactly the same distance away from the origin, and so this, the magnitude of x is r, which is a constant. Does That's set by r here. I don't mean the polar r. I mean just the radius of that sphere. Okay. And of course, we already had these constants, so they stick around for the ride. And we're left with just surface area. Surface area of the sphere. And you may recall this is a formula that I suggested everyone should know. I think everyone should know that formula. 4 pi r squared. So memorize if you haven't already memorized. Then conveniently notice that this r squared and that r squared cancel. And lo and behold, we are left with a nice simple formula for that flux. It's just negative 4 pi g m, where m is the total mass that's inside of that sphere. Which, of course, is the amount of mass that we concentrated at the center. How are we doing? Is everybody on board? Yes.
When we had like whole big density cloud thing, could we also just draw a bigger sphere and move all the mass to the center right there?
Well, yes, and that would be good for answering different kinds of questions, right? So we are going to, however, remember our original goal with this problem was to figure out what is the divergence at that specific point. Right, so we wanted the divergence as a function of position. So your strategy would be a good strategy for doing something different, but also worthwhile, but it doesn't help us get at what's going on right there.
Sure.
So, and by the way, we're not quite done yet.
Okay.
Yeah, I do have one more trick to pull before we really declare victory. But yeah, cool. Yeah. So we computed the flux. Now remember that per our discussion here, not our original question. Our original question was, what is the divergence at that point? I just computed the flux around a related sphere, and they're not the same, but here's how they're related, and that is this same flux. I can just apply Gauss's divergence theorem. Here, let me do it like this. That same flux, looking at the flux through that boundary, Gauss's divergence theorem says that, flux is a triple integral of divergence. This and there, the object that we're actually aiming for, the divergence of this insane gravitational field, has showed up. Keep in mind, we picked this to be a small ball here. And you can pick it as small as you want. The argument still applies no matter how small it is. So pick it arbitrarily small. Arbitrarily small balls have the feature that a function defined inside, continuous function defined inside of there is approximately constant. And so I'm going to just assert that as this divergence is approximately constant, it's a continuous function, teensy-weensy, itsy-bitsy little sphere, so it's not going to change very much. And in the limit, certainly, I can pop that outside of the integral. All that remains is volume, and we end up with that. So this flux being equal to that flux gives us the more relevant conclusion that that is equal to that. We were interested in divergence. Solve for divergence. And there's our formula for divergence. So we pulled it off, right? It's a ridiculous calculation. If we had gone, brute force straight at it, we never would have made it, right? For the related problem of flux, we have tools to work with. We have Gauss's divergence theorem. We have consequences of Gauss's divergence theorem about mass outside doesn't matter. Mass inside has flexibility of location. And then relate to what we're interested in, and out comes our conclusion. Okay. All right. So neat conclusion. So let's talk about this conclusion for a moment. The divergence of a gravitational field. No matter how much mass you have, no matter where that mass is, right? You could have a whole bunch of mass over there, creating a complicated gravitational field. I don't know. The divergence of the gravitational field only depends on what's going on near you. It only depends on how much mass, density specifically, is there near you. Everybody on board? Okay. All right. So now let's look back at this formula here. This formula, flux is negative 4 pi gm. This formula here only applies, we have to be delicate about this, as derived there. Our conclusion only applies to spheres. And why does it only apply to spheres? Well, look, we used that as a symmetry of the sphere right there. That's, importantly, only for spheres. And, area being 4 pi r squared. That's a sphere formula. All right, so this formula is sphere specific. However, this formula is not. This formula just says divergence. This isn't even about surfaces. This says whatever. Pick any gravitational field. This is what's going on at a single point. Looks like we're getting some pretty bad rain out there. Oh my gosh, there's people in boats. Wow. Okay. Whatever you want. Okay, so so this is not shape dependent. This is about any gravitational field. So what we're going to do is we're going to use this fact. This is arguably a more general fact then, and we're going to apply this now to an arbitrary solid with an arbitrary boundary surface. So now this is applies to any shape. Now there's a definition of flux. Gauss's divergence theorem. Don't forget, Gauss's divergence theorem applies. And we have that. So we have a triple integral of divergence. And on the previous page, independent of context, we know this always is true, that the divergence of the gravitational field, negative 4 pi g times the mass density. Okay. So does this help us? Well, yeah, it helps us tremendously. These are constants. They pop right outside of the integral. And I'm just left with a triple integral of density, which is mass. And look what we get. We get the same formula we had before. This looks like a reproduction, but again, very importantly, this is not a reproduction. What we have here is that a great extension. This formula that up here applied only to spheres, because we use specifics about spheres, now applies to any solid region with boundary surface. So that's pretty powerful. Okay, real quick before we get our hands dirty with an application, I want to talk about an interpretation that you can make of these last two results that we've just gotten. So, flux is proportional to mass. Got the gravitational field out there. Whatever the gravitational field is, whatever has created the gravitational field, I don't care. If you want to know how much flux there is through a boundary surface, just tell me how much mass there is inside of this surface. Mass inside of there tells me the flux. That kind of reminds us of a different physical scenario. Here's a scenario I want to remind you of. Let's consider this scenario. Imagine there's a light bulb right here where my fingertip is, right? Light bulb. It's shooting out photons, right? Think of photons as being a kind of a fluid. It's a fluid made up of particles. Then again, so is water. So this is I'm not asking a lot here, right? Light bulbs shoot out a fluid. Okay. Now let's consider a surface over here, a transparent surface, right? I don't want anything reflecting, right? Transparent surface. Here's the thing. Any photon created by this light bulb that goes into the surface will then just keep on going and subsequently go out of the surface. So this light bulb out here, because it's outside of the surface, the flux it will make through this surface is zero. Right? Where have we heard that before? That's just like the mass story. Right? Next question, let's suppose that I put a surface around the light bulb. Okay, well, every photon that shoots out of that light bulb will eventually make its way out of that surface. Right? And so, however much photons that light bulb is shooting out, that's how much flux there's going to be through the surface. And related, notice, if you move the light bulb a little bit, you move the light bulb kind of over to this side of the surface, well, okay, it remains that all of the photons leave the surface eventually. It doesn't really matter where in there that you put the light bulb. All the light gets out. Right? So again, so this is really very similar to the conclusions we've got here relating to mass. All that matters with gravitational flux is how much mass is there on the inside. All that matters in terms of light bulb photon flux is how many watts is the light bulb. Right? If you put a bigger light bulb, you're going to get more photons shooting out. You're going to have more flux of photons through your surface. Just like with the more mass. So the reason I bring up this example is because this formula, that flux is proportional to mass, is highly suggestive that maybe this is how gravity works. Right? People used to always, well, and this is still kind of a nasty problem, this whole action at a distance thing, right? If I push on this screen here, it moves. That I'm comfortable. It's that how did the thing move? Well, I pushed it. I touched it and then kept pushing, and that's why the screen moved. Right? But this action at a distance thing that by virtue of my having some mass, I am applying a force to that mass way over there. It's hard to see exactly how that works. You know what I mean? It's uncomfortable, philosophically. So anyway, this is a highly suggestive and tempting way to maybe resolve that seeming contradiction, that maybe the way action at a distance works is it's not really action at a distance. The mass that is me, right? I apply a gravitational force to that clock on the wall over there because my mass is shooting out little particles of some sort of the particles that are created by mass that are suggested by this flux formula, and that when that clock gets zapped by one of the little, they call them gravitons, one of the gravitons that shoots out of my finger or anywhere else on me, when that graviton hits the clock, that graviton is the thing that communicates and said, hey, gotcha, tag, you're it, there's gravity that's pulling you over this way. Right? So it's a way of kind of resolving the action at a distance quandary. And like I say, highly suggested by this formula. So anyway, that's pretty darn interesting, I think. And it all comes out of, ultimately, the thing that allows us to get to this conclusion is Gauss's divergence theorem. It's a big tool there. Okay. All right. So anyway, this is not a physics class, and all of what I just said about physics is, highly speculative, and this is not established, but it's pretty tempting. Okay. All right. So let's solve a problem. So let's think about a sphere centered at the center of the solar system, namely the sun, a radius of 100 million miles. Great big sphere. Let's think about what is the total gravitational flux through that surface. Well, there's a lot of planets. There's the sun itself. There's quite a few particles. There's a whole asteroid belt. Etc. Right? There's the whole galaxy. The galaxy is creating a gravitational field. It's not to be ignored, right? So if I want to know, with all of that mass combined, what is the total gravitational field? More precisely, what is the flux of that total gravitational field through this sphere? Centered at the sun, radius 100 million miles. what is that total flux? And the very first thing we do is observe that this is an immediate application of the formula above. Flux, negative 4 pi g times the total mass. So, fool you on Jupiter. Right? Jupiter is way further away than 100 million miles. So it creates gravitational field. Those field lines will intersect with this sphere, but they contribute zero flux. So we ignore Jupiter, Saturn, all those other planets and former planets out there, and other objects. The asteroid belt, that's all further than 100 million miles. Right? And there's only a pretty short list of non-trivial objects that are within this sphere. And let's see here. It is the Sun, Mercury, Venus, Earth, and Earth's moon. So add up those masses. These masses go in there, and negative 4 pi g times that. Everybody happy? Okay. All right. Here's another question. This is one of my favorites. I think this is really nice. Let's consider, this is a really hard problem, depending on how you look at it. Let's consider this arrangement of mass. This is a shell, a spherical shell of mass. It's got to be spherical. And of course, I'm only drawing a sort of a cross section of the sphere because otherwise we couldn't see what's on the inside. And I would like to ask the question, if you have a spherical shell of mass, now you might be thinking we're going to ask what's the flux of something, because that's the formula we have. But I'm going to ask a harder question. What is the field itself? What is the gravitational field created by this shell? So we're back to this intractably difficult problem of, come on. Look, there's that little piece of mass. It creates a gravitational field, and there's that little piece of mass. It creates a very different gravitational field, and there's bazillions of little pieces of mass. I've got to consider all of them and all the total of all those gravitational fields. How could I possibly do this? And it's a tremendously hard problem. So let me show you how everything falls into place. It's a wonderful argument. This is a spherical shell. It's a symmetric spherical shell by assumption. So this is, it's the same thickness, same density everywhere around. Okay. And the first argument I'm going to make is that means that the gravitational field has to have two key properties. The gravitational field has to be what I'm going to call radial. So you take a point there on a radial line coming out of the origin. The gravitational field, it wouldn't make any sense for the gravitational field to be like that, off axis. I mean, it's symmetric, right? You feel like because it's symmetric, as you turn this thing, the action of turning it, due to the symmetry, the action of turning it doesn't really change anything, right? You still got spherical shell with uniform distribution. So if the action of turning the mass doesn't do anything, how could the gravitational field be anything other than on axis? Furthermore, next fact I'm going to claim, this is just an intuitive appeal. I'm not getting rigorous about any of this. If you look at a point, the gravitational field, maybe it's something like that, let's say, and you look at some other point on this same sphere. So look at the sphere that goes through that point, centered at the origin. Look at some other point on that same sphere. Well, it's also going to be radial. God, that's the worst radial ever. Okay, there we go. It's also going to be radial. But it should have the same magnitude. Right, and again, I just appeal to your intuition about symmetry. It's a totally symmetrical shell. These 2 points are the same distance from the origin. How could it be more gravitational magnitude here and less gravitational magnitude there? They're the same distance away. They should be the same. That's just an appeal. Okay. Now here's an ugly question to ask. How do I know that this picture that I drew is even representative. I mean, I made an assumption here in drawing this that the gravitational field is inward. Are we sure the gravitational field is inward? Here, for example, let me try to make the case otherwise. Let's look at a point like that. Real close to one edge. Shouldn't the inverse square law mean that the gravity from the mass over here, look how close it is, right? Shouldn't there be just a lot more gravity from these pieces of mass? And opposing that, we have mass over here that's so much further away. Right? Maybe the gravitational field is outward when you get nearer the sphere. On the other hand, we have to admit that the closer you get, then there's also sort of the less and less mass is in actually pulling in that direction. This mass over here is really pulling that way, and its component in the direction, in the radial direction, is pretty small. There's just not that much mass there. By comparison, look at all of that. That's a tremendous amount of mass that's pulling, kind of generally, approximately in a radial direction. So this is a weird little tug-of-war we've got. We've got more mass at a greater distance. We've got less mass at a shorter distance. It's really not clear. Okay. All right. So anyway, I'm going to draw the field as being inward for no particular reason, and the arguments that I'm going to make would apply equally well if it went outward. Okay. So looking back at this sphere, considering a point, let's look at that sphere. Going through that point, let's consider the gravitational field. All of those points, all radial, all the same magnitude. And now let's simply apply our old result to this ball here. Okay. Our old result says that gravitational flux is equal to the total amount of mass that there is inside of this ball. Okay? So flux equals mass. Well, flux, constant proportionality. Flux is proportional to mass. Okay, now let me remind you the premise of this question. The premise is that we're looking at a shell of mass. So all the mass is over here in green. That's where the mass is. Inside of this yellow ball, there's no mass because the mass is all over here in green. So inside of this shell, no mass. No mass, no flux. That means that this gravitational field that I just drew here around this purple sphere, that flux has to be zero. Right? Now, how is that possible? How could it be that we've got a gravitational field pointing directly inward with as I have it drawn here anyway, a non-zero magnitude? That's going to compute a flux, a non-zero flux as I have it drawn. And that's not possible. Right, so my picture must be wrong. These field vectors here, they can't have non-zero magnitude. Non-zero magnitude gives a non-zero flux, suggests that there's a non-zero amount of mass in there, which there isn't. So these vector fields must have magnitude 0. So that means, because of that flux argument, that at this point, that vector field is actually 0. And that's a shocking conclusion. This applies, by the way, equally well anywhere in the sphere, right? I mean, there's nothing magic about that point. That was an arbitrarily picked point. You go back to this point near the edge here, you can draw a kind of analogous sphere. And the inside of that sphere is no mass. No mass, no flux. No flux, no gravitational field. At that point, the tug-of-war is tied. the teeny weeny little bit amount of mass that's really, really close, pulling really hard given its weight, right? That teeny weeny little bit of mass versus this great big mass that, well, it's too far away, per unit mass, it's not really pulling very hard, but there's so much mass. Perfect. Perfect tie. So I think that's kind of wild. Gravitational field is 0. By the way, you can make analogous arguments. I think y'all may have heard this one. A lot of people have heard the following argument of what about outside? What if you're there? As we are, right? If you could imagine a bunch of people on the surface of a planet, hypothetically, right? Then we are sort of just outside a great big spherically shaped arrangement of mass. Now ours isn't hollow on the inside, right? But analogous arguments. Think about what the argument would be for this sphere, right? The flux through this purple sphere depends only on the total amount of mass inside of it. It doesn't matter where the mass is. And so an argument that gets thrown around a lot is that you take something like a planet and you can treat all of the mass of the planet as if it were all centered at the center of the planet. Y'all heard this one before? Okay. Now, this spherical symmetry is critical there. We need for the gravitational field we have to agree that it was spherically symmetric in order to make this argument about how the no flux means that there's no gravitational field. So this does not apply to non-spherical planets. But hey, conveniently, planets tend to be spherical, right? So true fact then, analogous argument, the gravitational field that you experience standing on the surface of the Earth, you can calculate it by pretending that all of the mass of the Earth is located at the center of the Earth. All right, so I think that's fun. All right, moving along, I want to talk about electric fields. So some of y'all may have seen electric fields previously. If you haven't, you don't need to know coming into this course very much about electric fields and electric charges. Electric charges create an electric force. Two charged particles. It's kind of like gravity in a way. Two pieces of mass have a gravitational force between them. Two pieces of charge have an electric force between them. In fact, the analogies are extremely strong. This formula, notice, inverse square with distance, just like the formula for gravity. That's a tremendously strong relationship. And there's a bunch of constants all around there. But because it is inverse square with distance, just like gravity, the way we calculate, I'll say that the math of electric fields, it's morally identical to the math of gravitational fields. Different constants, yeah, sure. Of course, there's different constants that carry through the calculations, and they're just different. Right? But what matters is that inverse square, and these two very different physical phenomena, because they are structurally the same with inverse square, the math is all the same. So here's some results that we get. If you look at the electric field that's created by a point charge, the divergence is 0 away from where the charge is. If you want to know what is the flux of the electric field, through a boundary surface, it's 0 if the charge is entirely outside of the region. And on the other hand, if the charge is inside of the region, then the flux is independent of how those charges are distributed. Just like with the mass, you can put the mass inside the surface anywhere you want. You could put the charges inside of a surface anywhere you want. Doesn't make any difference. Just like gravity. And you can go through an argument not unlike what we did with the mass cloud. Remember, we had this cloud of mass, and we're trying to figure out what the divergence of the gravitational field is. Very cool calculation involving, a sphere and thinking about flux and using our previous results about what happens with the masses on the outside, masses on the inside. Analogous to that result, the divergence of the electric field is directly proportional to density. Well, now, not mass density. We're not talking about mass and gravity. Now we're talking about charge and electric fields. And so the divergence is proportional to the charge density. Charge per unit volume. Kind of like mass per unit volume, just with charge. Okay. All right. So one of the big takeaways I want y'all to get from, the applications that we're going to do in this course to electric fields is that electric fields are just like gravitational fields. It's different concepts. Here's one other important distinction, though, and I do have to point out, mass is all positive. There's no such thing as negative mass. Wouldn't that be nice? But there is no such thing, and so if you have two masses, they're both positive, and the way gravity works is it's an attractive force, and that's just how it is, right? Charge is different. There are positive and there are negative charges. So there's a plus minus to worry about. When you have two like charged particles, the way it works is it's a repelling force. It just is. Like charges repel. Opposite charges attract. That's just how the physics happens to be. Okay. But again, that's really just constants, right? Whether these two charges, Q1 and Q2, whether they're plus or minus, they're still constants. So structurally, we're still talking about inverse square with distance. Okay. So let's get some algebra on it. Here are the big results that you get. There's your formula for the electric field created by a charged particle. Notice it has this illusion of being inverse cube, but it's not. That's actually inverse square for the same reason as gravitational fields. Go through a fancy argument like we did with gravity. That's a great exercise, by the way. I think everyone should take a whack at that. Good. See if you can reproduce. Feel free to copy shamelessly, right? The arguments that we made with gravity. But try to, look at the arguments that we made with gravity. Try to, make what's the analogous argument with electric fields, and you will get to this analogous conclusion that the divergence is proportional to charge density. Just like with gravitational fields, the divergence is proportional to mass density. Same process. That's a fantastic argument exercise. I do want everyone to take a whack at give it a try. Try to fill in those blanks. Okay. And then related, the total flux is proportional to the total charge. By the way, and again, this is an immediate consequence of that, and we'll talk about how that works momentarily. But I do like to point out how this rolls off the tongue. It's really pretty elegant. This says flux is proportional to charge, right? This says divergence, okay, but let's say it differently. Flux density is proportional to charge density. So these two, if you interpret divergence as flux density, remember I'm a big proponent of this idea of thinking of divergence as flux density. Flux proportional to charge, flux density proportional to charge density. The linguistic analogy there emphasizes how closely related these formulas are. Okay. The next thing I want to talk about is I want to get into Maxwell's equations. And by the way, this is not a physics class, so we're not going to go very far into Maxwell's equations. But I want y'all to see how much of Maxwell's equations is wrapped up with Gauss's divergence theorem. And so these two equations that we have up here are called one of Maxwell's equations. And you might be thinking to yourself, wait a minute, that's two equations. See? 1, 2. Why is that called one equation? They're called two different versions of the same equation. And the reason why is because of how closely related they are. They're so closely related, it's like they're saying the same thing, just in different ways. And the linguistics kind of gets at that, right? Flux, charge. Flux density, charge density. It's like this is the density version of this one. They really say very analogous things. And so just as a reminder, let me point out how close these are in terms of mathematically. So I'm going to take this equation and take a triple integral of both sides. Forgive my sloppy notation there, but let's just take a triple integral of both sides, and let's see what happens to here. I have triple integral of divergence. Triple integral of divergence, according to Gauss's divergence theorem. Triple integral of divergence gives me flux. Right? And then, same thing. Let's look now, though, at triple integral of the right-hand side. Well, this little epsilon naught thing, that's just a constant that factors out. We have basically triple integral of a density. Triple integral of charge density gives me charge. We use Q to represent charge. So that's how closely connected these two equations are. These, in light of Gauss's divergence theorem, the connection is just take triple integral. A little bit of terminology. This equation, again, I'm going to use the singular. This equation, this is called the differential version of that one of Maxwell's equations. This is called the integral version of that one of Maxwell's equations. Okay. All right. And you can say a similar thing about magnetic fields. Again, that's not a physics class. So much we could say. We just don't have time, and it's just not the context. But magnetic fields are weird, and the divergence of a magnetic field is 0. That's just is. But so again, though, you can take a triple integral of both sides of this equation, and notice triple integral of divergence gives you flux due to Gauss's divergence theorem, right? And on the other side, triple integral of 0, of course, gives you 0. So again, we have two equations. These are considered to be a single equation. Two different versions of the same equation. They're about magnetic flux. This says magnetic flux is 0. This says magnetic flux density is 0. They're both about magnetic flux, just one as a whole, one as a density. Okay, so as I usually do, I'm going to skip this section, not because it's not something you should know, but because it's a pretty straight read, and it's highly analogous to Gauss's divergence theorem in R3. This is just how would you apply those same ideas in 2 dimensions. I'm going to ask you all to read this on your own. Like I say, it's pretty straight read, and it's what you understand about the 3-dimensional version will guide you through the 2-dimensional version. It's just a couple of pages. So do give that a read. You'll notice here's our picture of flux, right? Outward flux through 2-dimensional regions. And notice on the shared edge, right, that is that edge appears twice in a summation. Once oriented that way as part of D1, once oriented this way as part of the boundary of D2. So this edge appears twice, opposite orientations. They cancel. We keep seeing this same pattern, right? It's the same old story, slightly different context. The rest of the details y'all can read. Do notice the result ends up being that we have a familiar formula for divergence. It's the, when I circle this one, the formula for divergence in 3 dimensions, it's dp dx plus dq dy plus dr dz. In 2 dimensions, it's just take the first 2 of those terms. Couldn't ask for a nicer answer. If you were going to guess what divergence would look like in 2 dimensions, this is what you would guess. And it's true. Okay. All right. Okay. So let's move on to Stokes' curl theorem. This is our last boundary theorem. Remember, here in R3, this is our diagram in R3, and this was the starting point of our diagram in R3, and we've already considered this, the game here, where you take a boundary, find the appropriate operator so that these things end up being equal. That gave us the fundamental theorem of line integrals. And then we applied those same ideas over here last time, finished up today, taking solid regions with 2-dimensional boundary surfaces, and we found that divergence is what makes everything fit. So we're now just going to try to apply these same ideas here. So between columns 1 and 2. So what this means is we're going to consider now here in column 2, we're going to in 3 dimensions, a 2-dimensional thing is a surface. We're going to look at the boundary of that surface. You'll notice is a curve. So we're going to have a surface in space. We're going to look at the boundary curve. And we're going to ask, is there something that I can do to a vector field to make the boundary line integral equal to the corresponding flux through the original surface? Now, a lot of the words that we just said, we've never said like that before. But the pattern, right, this pattern is the rip-off pattern that we've done several times. So this is what we're hoping is going to work out. We just have to go through and play the game. See, do all the necessary ingredients come about. So we're going to consider now a surface. Here's a boundary, here's a surface. Some surface there in space. We're going to look at the, by the way, oriented. Notice, it's got to be an oriented surface. We're going to look at the boundary curve. And think about swirls. That boundary curve is oriented like that. And the big question that I have to ask is about accumulation. Is it true that if I chop that surface up into little pieces, and if I look on each individual little piece, if I look at the boundary, if I look at the boundary of each little piece, if I add up all of those individual boundaries, do I get the boundary of the original surface? Yes. The picture, it's so analogous, right? It's super analogous. That so here's one. Here is one little piece of surface, and its boundary consists of these 4 edges. Now, again, I could give these names and write this down in equations, but what really matters is I've got these 4 edges, and they're oriented that way as indicated. Okay. And then on the other hand, look over here, we've got this contiguous piece of surface there, and it has 4 pieces of boundary, and again, following the rules, swirls and all that. These are the boundaries orientations on its 4 edges. Notice, right on cue, this edge here appears twice. When I add the boundary of S1 plus the boundary of S2, I get this curve twice. Once oriented that way, once oriented that way. These 2 orientations are opposite; they cancel. I mean, again, we've seen this bunches of times already, so it's not really a surprise. I will point out that this picture that we've just drawn here looks kind of familiar. Doesn't it look kind of like the picture we drew for Green's theorem? I will point out that if you take a paper picture of Green's theorem, keep in mind, applies to just 2 dimensions. right? It's an intrinsically flat thing. But if you draw the picture for Green's theorem on a piece of paper, and then just pick up the piece of paper and kind of give it a little bend, right? Now, you've got a three-dimensional model of this picture for Stokes' curl theorem. It's so similar, pretty much the same picture. Everybody on board?
All right. All righty. So let's start writing down equations. A quick reminder, as we previously discussed, we're taking a surface, looking at the boundary curve. We're going to take a given vector field, and over that curve, we're going to look at the vector line integral, because that's
what the diagram tells us to do. Again, hoping that everything sort of fits together the way it's supposed to. Diagram suggests we should be looking at line integrals, vector line integrals of our given vector field around this boundary curve. And I call your attention back, your memory back to when we were talking about Green's theorem, and how can I think about this thing? What is a line integral around a boundary? And we talked about this term circulation. I remember circulation. So this is, in fact, a line integral of a vector field around a boundary. The boundary goes around. The boundary kind of makes a circle-ish kind of thing, right? If I want to know to what extent does my vector field flow along this boundary curve, we are asking to what extent does the vector field go around, to what extent does the vector field represent a fluid that is circulating.
all right. So we have circulation. Our goal is to ask, can I rewrite circulation somehow as adding up over the original surface, and even worse, somehow I have to interpret this as a flux. It's not clear how this is going to come up as a flux, but step one, can I think of these circulation as actually adding up over the surface? Well, I've already made this argument. I can add up over the individual pieces that I chopped the surface up into. So that gives me this. Notice the boundary of the original surface is the sum of the boundaries of the pieces that I chop it up into. That's what we could discuss previously. Now we're just writing down circulation on both sides. As usual, limits are free. I'm going to multiply and divide by area. It's because it's free. Notice that this expression now is looking a lot like a scalar surface integral. Now that's a little unsettling. We're not supposed to get a scalar surface integral, but that's kind of what I have, at least for the moment. Scalar surface integral. Again, I'm sweeping under the rug formalities and issues of regularity that we don't need to worry about in Math 212 because it all works out. So we end up then with this as our integrand for our seemingly scalar surface integral. And again, this is where, in previous cases, sometimes we got lucky and sometimes we didn't. Right? When we were thinking about the fundamental theorem of calculus, we were like, hey, limit of look, that's exactly the derivative. How about that? Cool. And then we just, write down derivative and celebrate. With the fundamental theorem of line integrals, we got to a point analogous to this and we said, oh, look at that. That's a gradient vector. How about that? Sweet. And we went on from there. With Green's theorem, we did not. Green's theorem, we had this formula of something like this, and we had to say, well, this is something that has to get computed, and I asked you all to take my word for it on how the calculation works out, and we have a formula for Green's operator. Likewise with divergence. I'm not going to show you those details. Likewise here. This is not something that we recognize. But do notice while we're at it, let me note that what we've got here is circulation per unit area. right? So when we were talking about the fundamental theorem of calculus, it was change per unit length. And we said, oh, let's call that change density. Okay. And in another context, it was, in Gauss's divergence theorem context, it was flux per unit volume. And we ended up motivating the idea of flux density through that. So I want to just plant a thought in your mind here that we're looking at circulation. Circulation is adding up. Circulation is accumulating over the surface, and it's an integral of what I'd like to call circulation density. Because look at literally what it is. It is circulation per unit size, area in this case, but size on the surface. So circulation density, very reasonable thing to call this. We'll come back and talk about that more in a couple minutes. But let's go to the calculation of what is this thing, and not gonna go into those details. But here is the result. There is a formula for it, and it's a little bit of a weird formula. Wish it were prettier than this, but this is what it is. And it's a complicated formula of various partial derivatives of the components P, Q, and R of our vector field. Remember, our vector field F has components P, Q, R. So you take P, Q, R, you have to take these various partials and assemble them as a vector. But then even weirder, notice my integrand, this thing, is not just something that's computed from those partial derivatives. You then have to dot it with the normal vector for the surface. And that seems to be strange, right? I mean, I'm interested in the vector field. Shouldn't this be something that depends only on the vector field? In most of our previous cases, it's been strictly a function of the vector field, right? Divergence is dp dx plus dq dy plus dr dz, period. That's it. It just only depends on the vector field. What's up with the dot product with the normal vector here? Well, I'm just going to make a quick physical kind of hand-wavy appeal, but keep in mind what we're looking at. We're looking at flux per unit area. Circulation per unit area, right? And if you have some vector field, imagine my vector fields represent flows of fluids, and so let's imagine a fluid that is actually circulating in some form or another. And I'm going to imagine a fluid that's kind of circulating around like this. You can imagine that the air might be sort of twisting around, something like this. If the air were doing that, and if I were to ask how much circulation is happening around my hand as I have it arranged here, well, it's circulating around the boundary of my hand. And I can talk about how much circulation per unit area on each little piece of my hand. But with the air circulating like this, now I appeal to your geometric intuition. What would happen if I asked how much circulation is there around my hand now, oriented like this? Well, the boundary curve of my hand is going around this way. But the air is circulating around that way, and it's just the air is not going around like this. The air is going around like that. Not the same. Right? So the quick appeal that I want to make is that how much circulation you get, and therefore how much circulation per unit area you get, should depend not just on the vector field, but it should also depend on, wait a minute, how is your surface oriented? Is your surface oriented like this? Or is your surface oriented like this? That's going to matter. So, plausible. The observation I'd like to make. Okay, so let's celebrate real quick and then we'll take a break. But here's our formula. Remember we had this seemingly scalar surface integral. There's what our integrand has turned into. And now notice it's no longer a scalar surface integral. In fact, it never was in the first place. That's why I kept saying seemingly. But now you can see that normal vector and that ds pair up and make ds vector. And in fact, it's weird, but I've actually got a flux of this little weird expression here. That's called the curl. This is called the curl of the vector field. So we have a result that circulation, boundary circulation, is a flux of a derivative of the original vector field, this being called the curl of the vector field. Okay. All right. So I just want to get this notation established, and then we'll call a quick break. Here's our formula for this thing called curl that we've got written down up there. Hope y'all remember we defined this independent little fellow here, the del operator. Right. It's a symbolic vector. Right. Just d by dx, d by dy, d by dz in three separate components. So you look at this formula for del, you look back at this formula for curl, and now do y'all remember the formula for cross product actually and structurally kind of in some ways reminiscent of this. And it just turns out, you got to write it down to check it out, but if you take del and our vector field F, and if you cross them, remember cross products are done by this symbolic determinant. And if you write down the formula for what you get as a result, this determinant turns into that formula right there, and lo and behold, in fact, you get exactly curl. So it's weird how this works, but this is another way of writing curl. That's a del cross. Strange, but true. Again, reminder, this is how I saw curl written in all my physics classes. It was written as del cross. Hardly ever, if ever, saw actually curl written with four English letters like this. Del cross is what you're going to probably see most of the time. Okay, so with that in mind, here's our original story. We took a surface, we looked at the boundary of it, and we looked at the resulting circulation, boundary circulation. We asked if we could write that as a flux. Turns out we did. We got this. It's this flux right here. Specifically, it's the flux you get by looking at this new operator, the curl of the original vector field, and I don't know why I did that in purple. I meant to do that in green. The flux of the curl of the original vector field, and you get a result here. Another one of these boundary theorems. Notice the pattern's identical to what we've done before. And I like to supplement that as here's our new diagram. There's that curl operator. Here then is the new theorem. This is Stokes' curl theorem. And the usual pattern. And our diagram keeps getting bigger. Okay, so this is a good place to take a break. See you all at 11:20. We'll start doing some examples and a few more applications.